Okay, so it's a great pleasure to have today's speaker, Aleksi Vuorinen, who is a very well-known name in the field of quark matter, especially in application of hard thermal loops to various problems, and recently to this neutron-star course. And he's also very well known as one of the co-authors of a very famous book on thermal field theory, which has an updated version now also. We are extremely happy that he would be telling us about this exciting field of research today. So Aleksi, over to you.
So thank you very much, Ayan, and thanks a lot for the invitation. It's very much a pleasure to be giving this talk. So indeed, as my title shows, I'm going to be talking about quark matter, but actually from two very different perspectives. So on one hand, from the perspective of thermal field theory, and in particular perturbative thermal field theory, and attempts to compute the equation of state or pressure of unpaired quark matter in perturbation theory. And then on the other hand, from the perspective of neutron-star physics and attempts to maybe locate or discover quark matter cores in neutron stars. And this work is based on a bunch of references given in here. One is actually very new, so this last paper on a sort of half thermal loop calculation of the, or perturbative QCD calculation of the quark matter equation of state just appeared a week ago or so. But good, when when we are talking about this kind of a topic, quark matter, then somehow the motivation, of course, comes from QCD, and in particular from a desire to map the QCD phase diagram. So a lot is, of course, known about this phase diagram, at least on a qualitative level. Maybe the most important single feature from the point of view of what I'm going to be talking about today is that when you increase the energy density, either by increasing the temperature or the density by a baryon chemical potential in your system, then you always at some point enter a deconfined phase. So at high temperatures and not very high densities, this deconfined phase is known as quark-gluon plasma. It can be studied, as you all well know, in experimentally in heavy ion collisions, where you can produce small fireballs of quark-gluon plasma that then decay, and by observing the particles and their properties, you can deduce something about the system that was created. But from a theorist's perspective, there's maybe an even more important thing in this hot and dilute regime of QCD matter, which is that we have a first principles non-perturbative method available for studying the properties of hot quark-gluon plasma, and that is, of course, lattice QCD. So we know by now things like, very robustly, things like the fact that the deconfinement transition at high temperatures and small chemical potentials is of a crossover nature, and it takes place at a temperature of roughly 155 MeV. But then when you proceed to the other end of this QCD phase diagram, high densities and relatively small temperatures, then you run into the physics of another type of deconfined matter called quark matter, and this time research on it, both theoretical and experimental, is quite a bit more challenging. So we do have, fortunately, laboratories where this kind of matter maybe can be found, namely the cores of massive neutron stars, the main topic of this talk. But unfortunately, due to the sign problem, we don't have lattice QCD available, so we will have to deal with other types of theoretical machinery and by sort of observations of neutron stars. Now, in neutron star physics, I would say that at least from the perspective of a QCD theorist, the underlying main challenge or main question is, can we determine the properties of cold and dense QCD matter using only first principles quantum field theory techniques, like, for instance, perturbation theory and so on, plus very robust observations of neutron stars. And here, of course, I'm kind of joining two very different worlds. On one hand, this microscopic world of particle interactions, in particular the interactions between individual quarks mediated by gluons, and then on the other hand, this macroscopic scale of neutron stars. And here the connection, as you probably well know, is offered by general relativity, and in particular, in the case of non-rotating neutron stars, by the famous Tolman-Oppenheimer-Volkov equations, which basically are two first-order linear differential equations that involve three quantities: the mass that is contained within a sphere of radius r from the center of the star, the pressure at that point, and the energy density at that point. And if we have one more relation between these three quantities that is typically given or assumed to be given in the form of the equation of state, the functional relationship between the energy density and pressure of this dense QTD matter that neutron stars are composed of, then we can just plug it here into this pair of equations. We can solve it from a given central energy density inside a star or central pressure, and then out comes basically a relation between the masses and radii of possible neutron stars. So this mass radius relation is typically given in the form of a curve on this mass radius plane. Here the x-axis is radii, the neutron star radius in units of kilometers, and the y-axis is the mass of neutron stars in units of solar masses. And if we knew precisely and accurately this equation of state, then we would be able to solve one well-defined mass radius curve, on top of which, at least in principle, every single simultaneous accurate observation of neutron star radii and masses would have to collapse on. But now it's probably not a surprise that things are not quite there yet. This is a very difficult problem, both from the perspective of QTD nuclear or particle theory, computing from first principles this equation of state, and then on the other hand, from the perspective of observational neutron star physics, it's very, very difficult to make precise simultaneous determinations of neutron star masses and radii, and hence, for instance, the current theoretical predictions for the mass radius curve and also the current observations are really not very accurate, but especially these theoretical predictions that you can see here are kind of all over the place. So what I would take from this is simply that there's a clear need for a systematic and model independence here is very important approach to the physics of QTD matter and to the microphysics of neutron stars. What I mean by model independence here is that what we don't want is a number of different, in principle, very precise predictions for the equation of state and mass radius relation that would lead to these different curves, mass radius curves in this plot, but rather what we would like is to have a model independent approach that then comes with where the predictions come with uncertainty estimates, so that we would really know how precisely we know these quantities, the equation of state and the mass radius relation at different points here. And this is indeed what I'm going to be talking about here today. But before I get to neutron stars and this sort of physics of dense QTD matter, let me make a small short detour to heavy ion physics, because very similar quantities than the ones that I'm going to be talking about today have already been sort of studied for decades in the context of heavy ion collisions, and it's clearly a worthwhile question to ask what we have learned from heavy ion physics. Now, this is of course a very wide and very active field, and by no means I'm able to sort of summarize it everything on one slide, but let me just take 4 individual lessons that I believe we have learned from heavy ion physics, both from experimental studies and from lattice and other theoretical calculations, and summarize them here. This choice is very much a subjective one, and I've chosen these 4 lessons because they are somehow they turn out to be very relevant and useful for the purposes of neutron star physics. So first, what I already mentioned briefly earlier is that lattice simulations have so far shown very conclusively that the deconfinement transition at high temperatures in hot and fairly dilute quark-gluon plasma is of a crossover nature. The transition happens at a temperature of the order of 150 to 160 MeV, which corresponds to an energy density of roughly 400 MeV over Fermi cubed. If we then keep increasing the temperature from here, then what happens is that the system, this sort of hot quark-gluon plasma, very smoothly but rather rapidly approaches behavior that can be described as conformal. And now what I mean by conformal is behavior where, for instance, the polytropic index, defined as the logarithmic derivative of the pressure with respect to the energy density, obtains very soon a value close to 1. The speed of sound squared approaches rapidly 1 over 3 from below, and the pressure divided by the temperature to the 4th power becomes proportional, roughly at least, to the number of degrees of freedom in the system. That, of course, in a conformal system are by definition massless. These are all well-known properties of conformal systems, and lattice simulations show that hot quark-gluon plasma is very soon after this deconfinement transition, already at a temperature of a few hundred MeVs, is behaving as an almost conformal system. Now a third lesson is that there are certainly some quantities, especially related to dynamical processes like thermalization, that are difficult to approach purely from a weak coupling calculation perspective. One might even argue that some quantities are easier to compute if one starts from the limit of infinitely strong coupling rather than zero coupling in the case of hot quark-gluon plasma. But there are also quantities, most importantly, these sort of so-called bulk thermodynamic quantities, like for instance the pressure as a function of temperature, where this is not the case. Rather, we know that for the pressure, for instance, and other thermodynamic properties, recent perturbation theory, calculations based on high temperature effective theories such as the hard thermal loop effective theory or electrostatic QCD, EQCD, and so on, they have been able to derive fairly accurate predictions for these thermodynamic quantities with controlled uncertainties already at temperatures of the order of 2 to 3 times the critical temperature, meaning something like 300 or 400 MeV onwards. And then finally, maybe on a more phenomenological level, I would say that one of the lessons that we have learned from experimental heavy ion physics is that when we try to, or if we want to know for sure that deconfined matter has been produced, for instance, in heavy ion collisions, it may well be that this information is most efficiently given by indirect measurements, by which I mean that when we first realized that quark-gluon plasma has been really created in the relativistic heavy ion collider at Greek, for instance, in BNL, it wasn't really that we observed some kind of a single smoking gun phenomenon that could only be explained by the presence of deconfined quark-gluon plasma, but it was rather that we were able to tell that some kind of at least approximately thermal system had been created where the temperature was so high that it was actually considerably higher, several hundreds of MeVs, considerably higher than the known scale of the critical temperature of the deconfinement transition. And therefore, sort of indirectly, we knew that we had created quark-gluon plasma at least for a very short time. And clearly, all of these lessons maybe could be generalized to neutron stars. This is actually exactly the topic that I'm going to be talking about today. So first of all, as I mentioned, we don't have lattice methods available in the case of very dense and cold QCD matter. So how can we remedy for this? On the other hand, then we don't have sort of laboratories on Earth where we could actually study this cold and dense QCD matter, maybe cold and dense quark matter, but rather our laboratories are located many light years away from us in space. How can we still exploit these very different types of observational information that, for instance, have something to do with the macroscopic properties of neutron stars rather than particles that are are detected in laboratories. And finally, maybe the most interesting and pressing question from the point of view of neutron star physics: do quark matter cores really exist in neutron stars? Do we have equine quark matter out there somewhere in the cores of massive neutron stars? And if we do, how can we tell? How can we ever know that quark matter cores exist in neutron stars if we can only measure properties like the macroscopic measurable properties of individual neutron stars? Good. Are there any questions at this point? If not, then let me continue from this kind of a more general introduction towards our sort of research, or the papers that I mentioned in the beginning. So let's next go to the question: what do we know about the neutron star matter equation of state from first principles? So by definition, I don't want to be using model calculations that may have uncontrolled uncertainties, but I really just want to be using very, very robust first principles or ab initio methods. Now, a very sort of reasonable starting point is then the region of low densities. So at low densities, when we're safely in nuclear matter and not in quark matter, then clearly trying to compute or determine the equation of state is a problem of nuclear physics rather than particle physics. And here I'm not really an expert of nuclear physics as such. I won't go to details of these calculations, but let me just say that this is at very low densities, this problem is essentially solved. The current state-of-the-art effective theory calculations employing typically the so-called chiral effective theory that uses the chiral perturbation theory power counting has resulted in an equation of state that is known up to some uncertainty of the order of plus minus 20% or so around the nuclear saturation density, 0.16 over Fermi cubed. So at the point when the number density of baryons is roughly the same as in individual large nuclei, then we know that the equation of state of dense nuclear matter up to an accuracy of roughly plus minus 20%. Now, there have been some attempts to even go beyond this, up to something like 2 saturation densities or so. We are actually being relatively conservative in using these results only up to 1.1 nuclear saturation densities. But when you go beyond this density, then the uncertainties in the results start to grow. And it's completely obvious that this is nowhere near enough, because the centers of massive neutron stars are expected to lie at densities of the order of 5 saturation densities or so. And clearly there is a long way to go from the current sort of nuclear theory results to where we want to be able to describe the entire neutron star.
Aleksi, I just have a
Yep.
clarification question. What do you mean by saturation density?
Roughly speaking, so the definition of the nuclear saturation density in this case is related to the sort of number density or even mass density of nuclear matter or very large nuclei. But in practice, what I mean by it is simply this particular baryon number density of 0.16 baryons over Fermi cubed, which is roughly speaking the same number density that you have in an individual proton or in a large nucleus, or equivalently where the inner core of a neutron star starts from. So it's basically, I mean, in very simple terms, you can think of that as the kind of density where if you are trying to describe nuclear matter, then you have to start taking into account in a very non-trivial way. I mean, well, of course, before that, you already have to start taking into account the interactions between individual nucleons. But at that point, roughly speaking, the nuclei or the nucleons are actually being squeezed inside each other. And at that point, that is exactly the point where this kind of power counting that chiral effective theory is based on, where you try to think of the degrees of freedom in the system as individual neutrons and protons, where their interactions are then mediated by pions and other light hadrons. This is no longer necessarily a quantitatively good starting point.
I see. So the criteria is simply the density should be the same as in a individual hadron.
Yeah, roughly speaking, yes. Okay, good. So this is sort of what we know about the low density side at this point. But then, of course, fortunately, this is not quite enough, or this is not nearly all that we know about QCD as such, because we also know that QCD is an asymptotically free quantum field theory, and at very, very, very high chemical potentials, at asymptotically high chemical potentials, we know that this equation of state the pressure as a function of the quark chemical potential, assuming, by the way, here local charge neutrality and beta equilibrium, so that everything really depends on one single quark chemical potential or baryon chemical potential. But very, very high values of this parameter, we know that this curve, the pressure has to approach this pressure of a free system of quarks, the Fermi-Dirac pressure of a free system of quarks. Now, this is again very nice to know in some sense, but it's not nearly enough. So we, on top of knowing what the asymptotic limit of this pressure or equation of state is, we of course also need to know how this quantity approaches this asymptotic limit. And here we don't have lattice QCD available, but one could at the very least hope that perturbative QCD methods would be useful in this limit, where in some rough sense we can assume that the system is weakly coupled, at least asymptotically. Now there are a couple of caveats here, and one of the more important ones is that we know that the ground state of high density quark matter at low temperatures is not unpaired quark matter, but it is some phase of paired quark matter. Asymptotically, it's very likely that color flavor blocked color superconductor, and then at moderate densities in the kind of quark matter that is likely or that might be realized inside neutron-star cores, it can be some more complicated phase of paired quark matter or color superconducting quark matter. Now, this is a real problem, I admit, but the good thing is that from the point of view of applications of perturbative QCD, is that since we are in any case most likely only able to use the perturbative results at very, very high densities, and we on the other hand know that the free or the pressure of unpaired quark matter, the pressure coming from the entire Fermi sphere of quarks, scales like the quark chemical potential to the fourth power, while the pairing contribution to the equation of state scales like the gap parameter squared times mu squared. It's actually a fairly simple exercise to know that at those densities that we will likely be able to use our perturbative results, the pairing contribution to the equation of state is at a per mil level or less than 1% level. So if we are going to aim at an accuracy comparable to the accuracy of the CET equation of state for nuclear matter around saturation density from high density PQCD, then it's probably not a very bad approximation to just ignore quark pairing effects overall. And indeed, this is what I'm going to do. Next, I'm going to describe briefly, or take another detour briefly and describe how we do these calculations at high density in perturbative QCD, and then very soon come back to how these results can be used in deducing this neutron-star matter equation of state.
Hello.
So for the time, yep.
Sorry to interrupt. Can you just say a little bit about what the quark pairing means?
By quark pairing, I just mean the exact same phenomenon that is responsible for ordinary superconductivity. So the fact that when you have a low density fermionic system, then the Fermi sphere is in the first approximation completely filled. States above this Fermi sphere are unoccupied, and then what happens is that individual quarks that are sitting on the Fermi sphere, meaning that their momenta are sort of located somewhere on the Fermi sphere, there's an attractive interaction between these quarks on the Fermi sphere, and these quarks form this sort of they so to say pair. They form excitations that then lead to the phenomenon of superconductivity. In the case of QED, that is ordinary electric superconductivity, and in the case of QT, that's called color superconductivity, because it's the color current that is sort of being conducted, so to say. And there's a large body of work by people like Frank Wilczek and Krishna Ratchagopal and Mark Alford, dating back 20 years or so, where they were systematically going through different pairing mechanisms and discovering that there are different types of color superconducting or paired phases in dense QCD, and due to the fact that this is the system here is fairly strongly coupled, it's not known exactly what is the physical phase at moderate densities. It's only at asymptotically high quark chemical potentials that Damson was able to show that the dominant phase is this so-called color flavor locked phase.
Okay, thank you.
But anyways,
so
yeah.
what is the quasi-particle in this case?
So now we are now we are sort of going way beyond my expertise.
Okay, never
but
mind.
It's
So
somehow
we can
so the
it's not a
effective theory
problem.
that you then have to write down is basically for sort of excitations of quarks whose momenta are roughly at the Fermi sphere, and then for these Cooper pairs that these individual quarks form. And I think these Cooper pairs are roughly speaking the sort of relevant excitations, but now we are going way beyond
Sure.
my expertise.
Yeah, not a problem. So, yeah, thank you. Yeah,
no worries. So good. So yeah, ignoring quark pairing for now, then let me just say a few words about sort of ordinary perturbation theory in the unpaired phase. So here, at least in principle, it's easy to write down what we are computing. It's really just basic equilibrium thermodynamics. So we work in the grand canonical ensemble. We are interested in the partition function, or the pressure that can be obtained from the grand potential. That's basically the logarithm of the partition function. In goes the Euclidean version of the QTD Lagrangian, and once you start then expanding this functional integral in somehow in powers of the gauge coupling G, you end up computing multi-loop vacuum diagrams. So really Feynman diagrams of this form in the first approximation at zero temperature and at non-zero quark chemical potentials. So this is of course technically fairly complicated, just how to actually compute these multi-loop Feynman diagrams. But then there is an additional complexity that you run into at three-loop order, and that is the sensitivity of these quantities to the phenomenon of dynamical screening due to long wavelength or soft gauge fields. And this, if you just start computing these kinds of individual Feynman diagrams, then at three-loop order you notice that there are uncancelled infrared diagrams or uncancelled infrared divergences in Feynman diagrams, such as this one in here. It's related to this sort of double gluon line here, which has the same momentum going through it. And if you just kind of take these graphs and compute them and don't do any kind of a pre-summation or use any kind of an effective field theory approach, then you are going to have uncancelled 1/epsilon infrared divergences in your final result. Now, of course, this problem has been solved to some extent before already. Friedman and Larry McLaren in the late 1970s were able to do this order G4 calculation by doing a very brute force computation of resumming these kinds of so-called ring diagrams, allowing the addition of more and more sort of gluon self-energy insertions on these soft gluon lines, which then produce the sort of order G4 or next to leading order pressure for this unpaired dense quark matter. But now we want to go beyond this because this accuracy is not quite what we would like. And at the moment, what we are doing is we are going at the alpha s cubed or g to the sixth next to leading order. And I won't go to the technical details of these calculations, but let me just mention that the different contributions to the QCD pressure or quark matter pressure can be basically divided to three different categories at this order. So there's first of all the contribution from hard modes of the scale baryon chemical potential, which can be determined by just computing vacuum Feynman diagrams up to four loop order. Then there's this soft scale related to this dynamical screening, where the relevant scale is the Debye mass at zero temperature, which is of the order of G times the baryon chemical potential. And then you also have to worry about the interactions of these soft modes, which is most conveniently done within the half thermal loop effective theory. And then finally, there is the mixing of these soft and hard scales. And as I said, I won't go to technical details, but let me just mention that the way to understand how these different scales contribute or one way of understanding how these different scales contribute is by looking at an individual four-loop Feynman diagram. So this diagram here is a vacuum four-loop diagram containing two individual quark loops, and this would be a very typical contribution to the pressure at order alpha s cubed. If all of these, so the quark lines here, these arrowed propagators, they are by construction hard because they contain the baryon or quark chemical potential scale, which is the hard scale. But then depending on whether these gluons here, there are four gluon propagators here, depending on whether they are soft or hard, this kind of a diagram can contribute either to the hard part of the pressure, the soft part, or the mixed part. If all of these gluon lines are hard, meaning that the momenta that flow along these lines are of the order of mu b, then this graph contributes to the hard contribution to the pressure, which we denote by a symbol P3H at this alpha s cubed order. But then if one of these gluon lines, say this one in here, becomes soft, then what you notice is that you can just keep adding these one loop sort of self-energy insertions, these individual quark loops to this one soft gluon line without increasing or without making this Feynman graph to be higher order. All of these kinds of contributions are of order alpha s cubed if this gluon is soft. And then what ends up happening is that you have to resum all of these kinds of diagrams containing an arbitrary number of these sort of gluon self-energy insertions until you run into a graph where you have a resummed HDL half thermal loop gluon propagator, and you end up with this kind of a three-loop mixed hard soft diagram that contributes to this mixed contribution to the pressure. Now, indeed, if this remaining gluon propagator here is hard, then this contributes to a term which we dub mixed or denote by P3M. But then again, if these two remaining gluon lines become soft, then you have to do one further HDL half thermal loop resummation, and then you run into or you end up with a two-loop half thermal loop effective theory Feynman diagram with not only resummed gluon lines but also resummed vertices. And this would then be a prime example of these soft contributions to the QCD pressure.
Aleksi, can I ask something?
Yep.
So there is a systematic way, as you're saying, of deriving an effective action,
Yes.
and because that helps us to make sure that we preserve gauge invariance and other things. So that's the point. And so the new thing that you're saying is that you need to also, in the effective theory, you also need to have this vertex corrections included. And could you elaborate on this part, that exactly what contributes to the vertex corrections? So I'm getting it only.
So first of all, I should say that this is nothing new. So the vertex corrections or the dressed HDL vertices are part of the HDL effective theory, and they have been known for sort of 30 years. I mean, they really were part of the initial work of Praten and Pisarski and so on, who devised the HDL theory. So this is as such nothing new. It's just that there have been very few calculations, if any, that have gone to high enough order in this full HDL theory that one would have needed to worry about these vertex corrections in individual diagrams. But certainly they have been considered in works by Mike Strickland and others, for instance, in the HDL perturbation theory context at high temperature. So this is not new as such. What is rather new is the way we compute these diagrams without ever expanding in these thermal masses. That is something that has never been done before. But yeah, did that answer your question?
Yeah. I was just looking for a bit more details on what is the machinery that.
Okay. So basically, this is So this is just ordinary half thermal loop effective theory. If you just want to know what these sort of effective vertices or vertex corrections mean, basically this blob means just the ordinary QTD unresound vertex plus then this one particular graph where you have this sort of quark loop out of which there are three individual external gluon lines, and you take the soft limit, you take the limit where all of the three external gluon lines are soft. If you take that limit in this particular graph, then you end up with this HDL vertex correction, which is actually a linear correction to the bare vertex. So unlike these propagators where you have to do a resummation of including an arbitrary number of these self-energy insertions, in this vertex function, this vertex function is literally just a bare vertex plus a one loop correction to it, nothing else.
Thank you. So this also can be understood from the point of view of this non-abelian Vlasov, this one loop that this quark loop. Yeah, okay.
Yes, absolutely.
Thank you. Good. And the new thing is simply the way you computed these diagrams and not this.
Yeah. Well, okay. So I would say that there are two sort of novel things. One is that this calculation just has not been performed at high density and zero temperature, but then the way that we technically do this calculation, we unlike everything that like Mike Strickland and his collaborators do in this so-called half thermal loop perturbation theory at high T. For them, so they go to a higher loop order, even in the half thermal loop effective theory, but then they do an expansion in the thermal masses, so they don't actually compute these resum diagrams. So keeping the self energies in the denominators of these resum lines, but we have to do this. This is just it's not that they do something wrong and we do something right, but it's that this application of ours requires keeping these I mean, if you want all the contributions to the QTD pressure up to order alpha is cubed, you have to keep these unexpanded. There's no way around that.
Okay, so another very naive question. So in the case of HTL, we have some matching with the lattice, and we know that it is fine up to 2 to 3 TC. So here, since there is no strict derivation, I guess, if I'm correct, it's simply a guess for systematic resummation. So in this case, what kind of check one can do?
I mean, so first of all, there's no guess involved whatsoever. So this is well, I mean, this is I mean, so the only difference to high temperatures is that we don't have lattice QTD to compare to. But what we do is we have all the contributions. So this is, I mean, there's a very important distinction between sort of half thermal loop perturbation theory type calculations that Mike Strickland and others do. What they do is they try to reorganize perturbation theory at high temperatures. So they, on purpose, they sort of try to include some higher order corrections to the sort of lower order, perfectly well-known pressure that they hope will sort of capture the most important physics from the sort of soft contributions and lead to a better converged result for the pressure. But what we do, we are not trying to make any kind of a so for them, in some sense, it's absolutely important that their final result contains kind of contributions up to an infinite order in chi. So they never, in the end of their calculation, they never do an expansion in powers of the sort of gauge coupling chi and then truncate the expansion at some order. By the way, if you give me just 1 second, I'll go and ask some other people to be quiet here because
Sure.
there's apparently very loud discussion here. So just 1 second. Yeah, sorry, sorry for this.
Fine.
Yeah. So what I was saying was that in these half thermal loop perturbation theory calculations at high temperature, they are really doing a reorganization of the weak coupling series, and on purpose, including sort of contributions up to infinitely high order in chi in their final result. While what we do is we use the half thermal loop effective theory as a tool to make sure that we keep all the contributions from the soft sector up to this order alpha s cubed. But our final result is really strictly an expansion in powers of alpha s cubed. So we don't include anything beyond this alpha s cubed order, but we do keep everything up to it. So this is a very important distinction.
I see. So in that case, there is not really a resummation. Actually, you could trust the result because it's not, no resummation is involved in that sense. That you
yeah. So I mean, yeah.
So systematic
yeah. So the point is that we want to have every single contribution up to alpha s cubed and nothing beyond that. And in order to capture all the contributions from the soft sector, we have to do a calculation in the HDL effective theory that you can, if you wish, call a resummation. It is a very concretely a resummation because, as you can see from these graphs, we sort of sum over diagrams at every order in these certain propagators. But this is absolutely crucial because the momentum that's flowing here in these kinds of diagrams, when you have the double lines, the HDL propagators, the momentum is of order g times mu, which is the same order as these self-energy insertions here. So this and all it's an easy power counting exercise to see that all of these graphs contribute to this same order. So we are not reorganizing the perturbative series, but we are doing a resummation to make sure that the soft contributions are all accounted for.
Thank you very much. Now it clarifies. Okay, thanks.
Okay, very good. And this was a very good question. I should actually mention. I think this is a point that is important to highlight in when talking about these calculations. So thanks a lot. This was a very good question. But anyways, coming.
Sorry, a naive question. So how important are these infrared contributions if you're interested in the total pressure?
I'm coming to this in a few slides.
Okay, all right.
So you will see momentarily. Yeah. So let me just sort of conclude that there are these three different types of contributions. The hard sector starts to contribute at order alpha is to power 0, the soft one at order alpha is squared, and the mixed one at order alpha is cubed. And before our sort of paper that came out 2 weeks ago, these terms. So everything up to order alpha s squared was known, but in practice nothing from these higher orders. There was, well, in principle, the leading logarithm at this alpha s cubed order was known. It was from a paper of ours a few years back, but it didn't account to any of these three terms in here. It was just a coefficient multiplying alpha s cubed times log squared alpha s. But now what we computed was this soft contribution at order alpha s cubed. So now we know exactly what this P3s here stands for, or how it reads, and from there we can also deduce the sort of leading logarithm at this alpha s order, the coefficient of this alpha s cubed times log squared alpha s, and also the soft contribution to the sort of next to leading logarithm. But in addition to that, we also know now the constant just number times alpha s cubed part that comes from this soft sector. And what then remains from a complete alpha s cubed order are, first of all, this mixed contribution. This we are currently computing very hard, and this is a very, very non-trivial calculation. I should, by the way, mention that if you look at these two papers, the first one is of the form of a 5-page letter, so you can certainly easily read that. But then the second one is 80 pages, and it contains all the sort of horrendous details of these calculations. And this is only getting worse when you go to the mixed contributions. I hope that later this year we will have that ready. If not later this year, then certainly next year. But then there is still this hard contribution at order alpha s cubed remaining, and there I don't dare to give any kind of an estimate on when we finish this, or even who finishes this. This is really a huge amount of work computing all the hard for loop diagrams in full QTD. But anyways, now coming to this question that concerning how important these different contributions are. So here I'm comparing the different orders in the expansion of the cold quark matter pressure, and this purple line here is what we computed now. So this is the soft alpha s cubed contribution. You can see that it's much more important, much larger than the soft alpha squared contribution, but it is not nearly as large as the dominant contribution at this point, which is basically the hard alpha squared term that has been known for quite some time already. But a simple comparison to the situation at high temperatures shows you that actually this high density, small temperature or zero temperature pressure is converging much better than the high temperature counterpart. And actually from here you can, at high temperatures, you see that roughly every second correction to the pressure has a positive sign, and every other contribution has a negative sign. And this is exactly the reason why these sort of reorganizations of the weak coupling expansion of the type that HDL-PT or the so-called EQCD resummation are designed to do are so important. So if one really expanded this high temperature perturbative result in powers of alpha s, the way that we have done here, the zero temperature high density pressure, one wouldn't get any kind of convergence until truly astronomical 10 to 10 MeV type temperatures. So yeah, the situation is much better at high density. And if you take this new result and plug it into the pressure, you see that actually the convergence of the pressure of dense quark matter seems to be improving. So we have not yet applied this to this sort of neutron-star matter equation of state calculations that I'm going to be describing momentarily, but at least at this point it seems these early indications of the result seem very positive. It seems that this new soft contribution is actually increasing the value of the pressure and taking the pressure closer to the free theory result, which actually improves the convergence properties of this expansion.
Sorry, what is the denominator here? The PFD.
Sorry.
What is the denominator? Delta P or PFD?
Okay. This is just the free theory pressure. So I'm always both in these kinds of plots and in here, I'm dividing the pressure by the free theory pressure. That's why somehow the so if you just did this calculation to one loop order, then you would get a flat line at 1, because by definition we are normalizing the quantity, normalizing the pressure with the free theory pressure. Okay, good. But now I'm actually running badly behind schedule. It's already almost an hour that I've been talking, and I'm only halfway in my talk, so I have to pick up my pace. So we have not yet applied these new results in this sort of study of the neutron-star matter equation of state. But if you take the previous state-of-the-art result from well, in principle Friedman and McLaren, but then sort of take into account the finite strange quark mass effects up to this alpha squared order, then you obtain these 3 green lines in this equation of state plot, which basically give you sort of in a summary give you an idea of what we know about this neutron-star matter equation of state today. So we have this quantity under control at low densities up to roughly the nuclear matter saturation density, and then at very high densities down to, roughly speaking, 40 times the saturation density. We have these PQTD results available, and the uncertainty of the result is the same at 40 saturation densities here at high densities as at 1.1 saturation density at low densities. And now what to take from this? There's clearly a sizable no man's land at moderate densities, moderate quark or baryon chemical potentials, and then one can either do what I didn't want to do, mainly use phenomenological models in between, or maybe ADS-CFT or something like this, or what I'm going to now be briefly showing you, you can also interpolate this neutron-star matter equation of state through this no man's land, and then use observational data to constrain the result. Good. So now I'm really running very badly behind schedule, so I'll be relatively brief now for the next 5 minutes or so. I'll show you something from what we know from neutron star observations, and I will briefly also explain you what this interpolation of the equation of state means. But then I want to spend the last I don't know 10 minutes or 15 minutes of my talk then sort of showing you our new results concerning the existence of quark cores and neutron stars and so on. But first, what do we know from neutron star observations? So the most fundamental quantity that relates to the macroscopic properties of neutron stars and is the most easy to sort of measure is the mass of individual neutron stars. And by now there are many dozens of neutron stars for which we have accurate mass measurements. And here by far the most important measurements are the sort of accurate measurements of the most massive neutron stars in existence. And here there are in principle 3 different stars that are very relevant. They are the so-called Demoresque and Antoniadi stars that are shown here as these two dots. And then there has been one third one measured lately with slightly larger error bars, which all point towards the existence of 2 solar mass neutron stars, meaning that the maximal mass of stable neutron stars exceeds 2 times the mass of our sun. Now, why is this so important? It's important because this single observation in principle means that we can discard all those equations of state for neutron star matter that lead to mass radius curves that don't actually exceed this red horizontal line in here. So this alone is very valuable. Then there's of course neutron star radius measurements, but these are much more complicated. So this is we won't actually be using any of these results in our calculations, but I should just mention that there has been quite some progress lately, and we have very high hopes on the NICER project in providing the sort of a robust radius measurement for a sort of neutron star with a fairly accurately known mass in the near future. So what these radius measurements tell us right now is that very likely the relevant order of neutron star radii is something like 12 kilometers. Still maybe 10 years ago, it was thought that neutron star radii could be smaller than 10 kilometers or larger than 15 kilometers. Now we know that most likely they are between, say, 11 and 14 kilometers, maybe most likely around 12 kilometers or so. And this is already very valuable, but the uncertainties are big enough so that right now we are not really able to use this input in our calculation. But then finally, there is of course the gravitational wave measurements from LIGO and Virgo, which is of course incredibly famous and has led to many applications. And here, let me just briefly mention that there are 3 types of potential inputs from these gravitational wave measurements. They are the tidal deformabilities that have been measured that give us very nice constraints. Then there are the sort of simultaneous possible electromagnetic measurements that may tell us something about whether a black hole was created in the merger process or not. And then in the future, hopefully we will be seeing also a ring down pattern, so a measurement of the part of the merger where the 2 stars have already collided and they are then sort of merging and finally maybe the system is collapsing into a black hole. But right now there's only one of these 3 things that we really fully have available, and that is the LIGO and Virgo measurement of the tidal deformability in this GW170817 merger. So what the tidal deformability is, it's a parameter that basically tells us how susceptible the structure of a neutron star is to external quadrupolar gravitational fields. It's basically a sort of linear coefficient in a relation that tells you how large of a quadrupolar component the star's own gravitational field becomes when the star is immersed to an external quadrupolar gravitational field. And so in sort of more concrete terms, this has to do with the size of the tidal forces or the magnitude of tidal forces and their effect in neutron star mergers. And the important thing is that in GR or relativistic hydro simulations of neutron star mergers, it has been shown that large values of this tidal deformability parameter have a visible effect in the waveform that is detected by the gravitational wave observatories. And since this effect was not very large in this 2017 event, LIGO and Virgo have been able to basically give us a 90% confidence interval for what the tidal deformability of a 1.4 solar mass star is. And this is very valuable because this tidal deformability quantity is something that we can, given any equation of state, we can just go on and compute this number in suitable dimensional units, and we can, just as we can discard those equations of state that don't support 2 solar mass stars, we can also discard those equations of state which lead to tidal deformabilities for 1.4 solar mass stars that are larger than this upper limit 580. Okay, very good. So then this naturally brings me to this interpolation approach of ours, which is basically the method by which we try to combine this knowledge that we have of the kind of limiting properties of the neutron star matter equation of state at low and high densities, and on the other hand then these astrophysical observations. So here again I'll be quite brief. What we do in practice is we take the chiral effective theory EOS at low densities or low baryon chemical potentials. We take our PQCD result at high densities, and then in between we divide the baryon chemical potential region in between to several pieces, and then we build interpolating functions, randomly generated interpolating functions in between. And this way we come up with large ensembles of possible neutron star matter equations of state that might look, for instance, like this once we generate of the order of several hundreds of thousands prototypical neutron star matter equations of state. Now these interpolated EOSs, they are required to satisfy some sort of requirements, including a smooth matching to the low and high density equations of state, because we don't expect there to be a phase transition at such low densities or such high densities. We also demand that the pressure and baryon number density are continuous, with the exception of one point where we allow for the baryon density to jump, so that we can mimic a first order phase transition. We also demand that the speed of sound is below 1, below the speed of light, and then we can go on and take into account different astrophysical observational constraints. Now, just to briefly show you the results of such a procedure, these are the equation of state and mass radius clouds that one obtains in this fashion. This is from a 2018 PRL that we wrote with Emily Annala, Tyler Gord, and Aleksi Vuorinen. These clouds are still fairly sizable, but then we can go on and start taking different observations into account. The first and simplest observation is simply the existence of two solar mass stars. That lets us get rid of this region of the mass radius cloud that corresponds to equations of state that are very soft at low densities, and this then also simultaneously rules out very small radii at for instance 1.4 solar mass neutron stars. Then we can use this tidal deformability constraint by LIGO that helps us get rid of exactly the other end of the equation of state spectrum, those equations of state which are very stiff at low density, because they would lead to very large neutron star radii and large values for this tidal deformability parameter. And finally, we can keep playing this game. We can also ask what would it mean that if we obtained an accurate radius measurement for a star with a well-known mass. For instance, here we show what would happen if we knew that a star of 1.9 solar mass had a radius between 12 and 12.8 kilometers. So clearly, these kinds of measurements would also be very, very helpful. But since this is not really new, I don't know how much more how much time do I have still?
Actually, you just completed an hour, so you can certainly take 5-10 minutes more, I guess.
Okay, good. Yeah, thanks a lot. Yeah, in 10 minutes I will be able to go through the last part of my talk. Yeah, so what I definitely want to still show you is results from recent work that was published in Nature Physics last summer, where we continued along this sort of equation of state interpolation direction, but now we started from interpolating the speed of sound squared of neutron star matter as a function of baryon chemical potential, and then this helped us classify our results in a slightly different way. Now the reason we are interested in the speed of sound is basically because there is a strong tension between the sort of common law in the nuclear physics and astrophysics community and in other fields of physics. So in nuclear physics and neutron star physics, the general assumption is, and has been for decades, that the speed of sound has to take very, very high values. Actually, most model equations of state for nuclear matter lead to neutron star matter, or lead to speeds of sound in neutron star matter that grow up to the speed of light, and even above that in some cases, which is clearly unphysical, while we know from other contexts, for instance from lattice studies of hot quark-gluon plasma, that it is actually extremely rare in nature to have physical systems even exceed the conformal value of CS squared equals 1/3. So for instance, in hot quark-gluon plasma, we know that while the speed of sound is not really a monotonous function of temperature, but in the quark-gluon plasma phase, it actually is a monotonously increasing function that approaches this 1/3 value from below at high temperatures. And this has even prompted some people to speculate that this conformal 1/√3 limit might act as some kind of a universal upper limit for the speed of sound, in the same way that we have the famous E over S equals 1 over 4 pi as a conjectured lower limit for the shear viscosity over entropy ratio coming from ADS-CFT. Now what we then did is what we basically repeated this interpolation calculation. We computed the pressure eventually as a function of varying chemical potential and energy density in here, but now keeping track of the speed of sound in QTD matter. So this allowed us to ask the following question: what would the band of allowed equations of state look like if we knew that the speed of sound squared never exceeded a value, for instance 1 over 3, a conformal value that's represented by this dark blue band here, or 0.4, 0.6, 0.8, or 1. And what this clearly shows us is, if we had this extra information that the speed of sound squared never becomes very large, that would have an enormous impact on how constrained the neutron-star matter equation of state is. And furthermore, if we knew that the maximal value of CS squared at any density was never larger than, say, 0.4 or 0.5, we would start to get a form of EOS band that would be very reminiscent of kind of a two-phase structure, by which I mean that if I just take the low-density chiral effective theory EOS, continue it with a straight line, and on the other hand take this high-density PQCD equation of state and continue that with a straight line in this logarithmic plot, I would get an approximation for this low speed of sound bands that is actually not too bad. And clearly, one is very difficult, at least for us to not to help and not think about this observation as an indication of maybe something happening in this kink region in here that is reminiscent of a phase transition between nuclear matter and quark matter. And indeed, if we overlay in this plot the predictions of all the different nuclear matter model equations of state that are consistent with all astrophysical observations, then we see that almost all of these just continue with exactly the same slope, meaning the same value for this polytropic index gamma, the logarithmic derivative of the pressure with respect to energy density of about 2.5, that is characteristic for low density nuclear matter. While starting from high densities, if we go down, it seems that the slope of this EOS band is staying at a value very close to unity until much lower densities than where we use this PQTD result. So clearly there are some obvious questions that we need to answer. One of these is whether this two-slope structure is only a property of these low speed of sound bands, or does it persist when we look at the equations of state one by one, and does it also persist when we allow for larger values of the speed of sound squared? And also, obviously, where do the centers of neutron stars with different masses lie in this band? Meaning, do they lie, especially do the centers of maximally massive stable neutron stars lie to the left of the kink, suggesting that they are composed of nuclear matter, or to the right of the kink, suggesting that they might actually contain quark matter cores? Now, to answer these questions, we then systematically compared all of these interpolated equations of state of ours to these nuclear matter equations of state that I'm showing here. So what does the result look like? So here I'm first plotting these nuclear matter equations of state, so the predictions of nuclear theory, in a three-dimensional plot where the axes are the pressure divided by the Fermi-Dirac pressure, the speed of sound squared, and the polytropic index gamma. And what you can see is that when we start from low densities and keep increasing the density, all of these nuclear matter EOSs correspond to or predict an increasing value of the speed of sound squared that obtains maximal values of the order of 1. And also when we overlay the centers of 1.4 solar mass neutron stars and maximally massive neutron stars, they form two very distinct sort of regions in this plot. Now, including here or adding here all of our interpolated equations of state or a representative subset of those, we see that the most important difference from these nuclear matter EOSs in our case is that our equations of state really eventually end up in this PQCD region as they should. But now what is I would claim even more important or interesting is that when we add the centers of 1.4 solar mass neutron stars and maximally massive neutron stars to this plot, we see a perfect overlap for the 1.4 solar mass neutron stars, or their centers in here, but an almost non-existent overlap for the centers of maximally massive neutron stars. So in our interpolated equations of state, the centers of maximally massive neutron stars lie considerably closer to the PQCD regime than to the regime of hadronic matter. And this observation persists if you take two-dimensional projections from that 3D plot, and clearly the centers of maximally massive neutron stars really form two disjoint groups here in this plot, and this suggests maybe that one could perhaps use this gamma, the polytropic index, as a sort of approximative criterion dividing quark matter from nuclear matter. By this, I simply mean that we know that in nuclear matter, the polytropic index is typically of the order of 2 to 3. In conformal quark matter, we know that it's exactly 1 or very close to 1. So let's just draw a horizontal line here at the average of these two values at gamma equals 1.75, and sort of for the time being call matter sort of corresponding to a gamma value below 1.75 as quark matter and above 1.75 as nuclear matter. If we do this, we obtain a sort of very sort of suggestive plot or result. Here we are asking the question, if we look at only maximally massive neutron stars and we group and we define quark matter in the way that I just explained with this polytropic index, how large is the size of a possible quark matter core in maximally massive neutron stars? It turns out that if unless we allow for very high values of the maximal speed of sound squared and simultaneously strongly first order phase transitions, these maximally massive neutron stars are bound to have sort of non-zero quark matter cores. It's only if we allow simultaneously CS squared to exceed the value 0.7 and the latent heat of a first order phase transition to exceed a value of the order of 200 MeV over Fermi cubes that we can have maximally massive neutron stars completely composed of matter corresponding to gamma larger than 1.75. And this is well, what you make of this is of course a matter of taste to some extent, especially this definition of quark matter via this polytropic index is something that is of course debatable, but I think this is at the very least an indication that matter in the centers of maximally massive neutron stars has very likely properties fairly close to what we expect from quark matter. And finally, let me just show you very recent results that are actually not even out yet. Hopefully these will come out still this month or next month. If one additionally takes into account the fact that a black hole was very likely produced in the GW 1708-17 event, then we get even sort of more constrained equations of state, and we automatically get a maximal mass for neutron stars of the order of 2.2 solar masses. But actually this time there's no huge impact on the sort of likelihood the existence of quark matter cores. But in any case, I dare to claim that somehow continuing along this trajectory that we have started, and with the with incoming new observations concerning the masses and radii of neutron stars and their and gravitational waves coming from the emergers, I think it's quite possible that we will be able to conclusively determine whether quark matter cores exist in neutron stars in the next 5 years or so. Good. So as I'm badly running out of time, I will just stop here instead of going through these sort of final thoughts. Thank you very much.
Thank you, Aleksi. Thanks for this great introduction to your research and also giving us the latest results on what you have got or what is going to appear. So it's time for questions now. Let's have a few.
Yeah, sorry for going so badly over time, by the way.
Well, we had questions in between. It's normal. So this is the usual time that we take anyway.
Okay, good to know.
Yeah.
Can I just ask one thing about the infrared contributions to pressure that you talked about?
Yes.
So just wondering, that turns out to be substantial, right? I mean, if I got the message from that plot.
Well, yeah. So in the case of hot quark-gluon plasma, these are extremely important. So if you look at this, I didn't have time to discuss these results in so much detail, but actually, if you look at this, the case of hot quark-gluon plasma, then you see that systematically, order by order, it is the soft infrared contributions that are most important, and this is exactly what then leads to this bad convergence of the weak coupling expansion and the necessity of doing these resummations. But in the case of cold quark matter, this is not quite so. So in here, if you just look at the magnitudes of these different contributions, it seems that the hard contributions are still larger than the soft ones, even though at this alpha s cubed order, the soft contribution is already comparable in size.
Yes, so it's about 1/4 or something. It's not that.
Something like that, yeah.
Yeah. So just naively, is that because of the number of such soft gluons? That's what beats the low energy? Is
that's an excellent question. So this is, it's not, I mean, so what one would be tempted to think that this is somehow related to the number of degrees of freedom, but at these kinds of coupling strengths that I'm showing here, it's not obvious that one can make that conclusion. So because it's strictly speaking, it's only at sort of, I mean, this whole statement of the number of degrees of freedom dictating or the pressure being proportional to the number of degrees of freedom. This is strictly speaking only valid at densities or high enough so that the system truly is conformal or at least somehow weakly coupled, and this is not quite the case in here. So I think this hot QGP case is exactly a counterexample, because the number of soft degrees of freedom should be quite a bit smaller than the number of sort of hard degrees of freedom, and what's likely happening in here is something else. So it's, I think that in this particular case, this bad convergence is rather related to the behavior of the Bose-Einstein distribution function as a function of energy, in the sense that you can actually argue that at high temperatures, the relevant expansion parameter is basically in the weak coupling expansion is basically the Bose-Einstein distribution evaluated at the sort of typical scale of your excitations times alpha s. And now for the soft scales, this energy scale is either g times t or even g squared times t. And this then, when you plug this into the Bose-Einstein distribution, you can see that for the soft modes, the expansion parameter is not of the weak coupling expansion is not alpha s, but it's square root of alpha s. And then there's even this ultra soft scale g squared t, for which there's no weak coupling expansion at all, but there's a non-perturbative contribution from these ultra soft sort of static magnetic fields, and this leads to the well-known Linde problem at high temperatures. And I think that what is happening in this case, at the very least, is not directly related to the number of degrees of freedom.
Okay, thank you.
Okay, so Aleksi, I just have a very short question. So since in this case the expansion, the HTL expansion is very good, very well convergent. So this alpha s to the power 4 is not that important to compute, or it will have significant impact on this interpolation.
So there's actually now, I mean, one could approach your question in from multiple angles. So if we think about this from the perspective of these interpolation calculations, the neutron-star matter equation of state, then actually what would have a humongous impact is if we were able to improve the convergence of this expansion, so that we could make this matching point, that the matching that we do in here, if we could move this matching point to lower densities by sort of improving. I mean, what you can see is happening in here is that this lowest green line that corresponds to the basically this lowest value of this x parameter, which is proportional to the renormalization scale of that any finite order perturbative result depends on. If we can somehow obtain a higher order result where this lowest lambda bar limit doesn't start diverging at such high densities, then this would really improve this whole interpolation calculation. So I wouldn't say by any means that this is not important. So we can see already from here that that this kind of soft alpha s cubed result already has a visible impact on the equation of state. And what we of course hope would happen is that once we determine this mixed contribution and certain parts of this hard contribution that allow us to get rid of a dependence of our result on an unphysical parameter that shows up in these kind of minor bands in here. It just could be that somehow this entire pressure band would have a significantly narrower extent after the inclusion of these new orders. And if this is the case, that would very much impact such interpolation calculations. If we were able to move this matching density from 40 saturation densities down to 30 or maybe even 20, that would immediately improve our accuracy a lot, really substantially.
So Aleksi, just asking, is in the HTL case, if I remember, there was alpha s to the power 6 was sort of a bottleneck. Is there some kind of bottleneck you expect here, or just naively?
Sorry, I didn't quite catch you. What was the bottleneck?
If I remember, alpha s to the power 6 was sort of a bottleneck in the HTL story.
Okay. So first of all, it's alpha s cubed that people are going at. So if you're referring to high temperature calculations, actually this the half thermal loop perturbation theory calculations are only valid to alpha s squared. So it is rather the work of Nikkolainen and Keijo Kajantie and others, where they were able to go up to g to the 6th log g. And what they have computed there is everything, all the contributions to the high temperature pressure, with the exception of this hard part. So once we have computed this PM3 term, then we are exactly at the same order at high density and zero temperature than people have been at high temperatures already since 2005 or 2006. But then we run into the same issue, that both in the high temperature case and in this high density case, if one wanted to complete this alpha s cubed order, one would need to compute all of these for-loop vacuum diagrams, and that is an extremely complicated thing. So this is the reason why this is so difficult is basically that when you have finite temperature or non-zero temperature or density, then you lose all of this very nice machinery of zero temperature vacuum perturbation theory, where people can use integration by parts identities and many other techniques, because you have this sort of extra scale involved. And of course, York Schroeder is the person who has been trying to do this, or who has been devoting the largest amount of time to this high temperature multi-loop calculations. And as far as I understand, there hasn't been much progress in the past 15 years or so. And well, there are some indications that things might be a bit simpler in the case of zero temperature and high density. The purely gluonic diagrams, for instance, completely vanish. You need to have at least one fermion loop in all the Feynman diagrams, but still, this is going to be really tough. This is not something that one is able to do in the time frame of a few years.
There is an analog.
Yeah.
That's what you're saying. There is an analog of the master integrals in vacuum diagrams.
Yeah. There's a shitload of master integrals, and there are very few techniques in existence that would allow one to tackle them in any kind of an automated fashion, which is really what is needed at that point.
Yeah. Okay, so let's see if there is a quick question or some other from.
If there is time, can I ask one more?
Sure.
Just wondering about the first order phase transition that you mentioned. How, with what certainty or how reliably is it known that it is first order?
Not at all. So the point is that in all of these interpolation calculations of ours, we use the first order phase transition and its strength or the existence and strength of a first order phase transition as a free parameter. So what we know is that at high temperatures there's a crossover transition, and there are some model calculations suggesting that at high density and zero temperature there would be a first order transition, and therefore there would be a critical point on the QCD phase diagram. But this is not based on any robust first principles argument. So it can be that there is a crossover transition also at high density, or there can be a weak first order transition, or there can be a strong first order phase transition. And since there's no clear perturbative, or not perturbative, but theoretical argument suggesting that what the order and strength of the transition should be, we want to be very conservative, and we allow everything. We allow both a crossover transition or a weakly first order transition and strongly first order transition. We keep the latent heat as a free parameter.
So the lattice computations don't tell us one way or the other with any certainty?
No, there's this famous sign problem that lattice QPD suffers from, and therefore it's useless here.
All right, thank you.
No worries.
Okay, so it has been quite a while then, and it's getting late here. So we should thank Aleksi for giving this nice colloquium and introducing us to this really fascinating topic. And
thank you very much.
So have a nice day, Aleksi, and thanks to everybody for joining in.
Thank you very much.
Yeah, thanks a lot, and yeah, I really hope that we get to see each other soon enough in some conference. It's been quite a while since traveling has been possible.
Yeah, please come and visit Chennai.
Yeah, that would be great. Yeah, once probably is possible.
Once it is possible.
Yeah, and same here. It would be nice to have you visit Helsinki.
Thank you. Okay, have a nice evening, all of you,
You
and
too.
goodbye.
Bye-bye.